Hello, in today's lesson we're looking at Chapter 9, Section 1, Similar Right Triangles. Our objectives are to solve problems involving similar right triangles formed by the altitude drawn to the hypotenuse of a right triangle. We're also to use the geometric mean to solve problems. Theorem 9.1. If the altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. As a quick refresher, altitude is the perpendicular distance created from the base of a triangle to the opposite vertex. So remember, the altitude is the same thing as the height, and it creates a 90-degree angle from the base to the opposite vertex. In this triangle, we can see three different triangles. There's one big triangle, which is ABC. We also have a medium-sized triangle, which is ACD, and we also have a smaller-sized triangle, which is CBD. When writing our similarity statements, there's three different ways that we can write it. We can say that triangle CBD is similar to triangle ABC. We can also say that the mid-sized triangle ACD is similar to the big triangle ABC. And finally, we can say that the tiny triangle, or the little triangle CBD, is similar to the mid-sized triangle ACD. Example number 1, finding the height of a ramp. A ramp has a cross-section that is a right triangle. The diagram shows the approximate dimensions of the cross-section. Find the height h of the ramp. So we're going to use Theorem 9.1, and we can use that because we have a right triangle that is divided into two smaller right triangles. In order to write the proportions, I need to first write the similarity statement. So I'm going to start by looking at the big triangle JKL. I'm starting at the vertex of my short leg, going through to the right angle, going down to L, which is the long leg, and then my hypotenuse over here. I've got triangle JKL, which is similar. I'm going to use the little triangle over here, KML, again, so that I'm matching these triangles or mapping them onto each other. In triangle KML, I'm going to start at the short leg, go down to my right angle, and then through to my long leg, and then up the hypotenuse over here. So I'm going from K to M to L, which gives me triangle KML. So my similarity statement is triangle JKL is similar to triangle KML. Once I have this, now I can write my proportions. I know KM maps to JK, and since I use triangle KML on top of my first ratio, then I'm going to put triangle KML on my second ratio to create that proportion. In this case, I know the length of KL, so I'm going to say KL over JL. Once I do that, I fill in what I know and what I need to find. I know KM is H. I know that JK is 4.7. I know that KL is 11 and that JL is 11.7. Cross multiply, I get 11.7 times H is equal to 11 times 4.7. Isolate H by dividing both sides by 11.7, and 11 times 4.7 divided by 11.7 gives me approximately 4.4. So the height of the ramp is about 4.4 feet. Alright, checkpoint problems number 1 and 2 are yours. In both of these problems, you are to write a similarity statement for the three triangles in the diagram, then find the given length. Round decimals to the nearest tenth if necessary. Geometric mean theorems. Theorem 9.2. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of the altitude is the geometric mean of the lengths of the two segments. In Theorem 9.2, we're actually comparing triangle CBD to triangle ACD. And we can say that BD over CD is equal to CD over AD. I know that this can get confusing, so one thing I like to do is I like to redraw these triangles. So we have triangle CDB over here. C to B is my hypotenuse, C to D is my altitude, and D to B is my short leg. I am going to rotate ACD so that it matches with triangles CBD. So it's going to look something like this, where A to C is my hypotenuse, A to D is my altitude, and D to C is my short end. So if I'm looking at this proportion over here, BD in this triangle is my short leg over CD, which is my altitude, and that's equal to, in this triangle, the short leg, CD is the short leg, over the altitude, which is AD. So that's how that matches up and how we got that proportion. Theorem 9.3. In a right triangle, the altitude from the right angle to the hypotenuse divides the hypotenuse into two segments. The length of each leg of the right triangle is the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse that is adjacent to the leg. We can say AB over CB is equal to CB over DB. And in this case over here, we are comparing triangle CBD to triangle ABC. AB is the hypotenuse of the big triangle over CB, which is the short leg of the big triangle, is equal to CB, which is the hypotenuse of the little triangle, over DB, which is the short leg of the little triangle. And this part over here, AB over AC, is equal to AC over AD. This one is comparing triangle ACD to triangle ABC. So looking at the big triangle, we got AB, which is our hypotenuse, over the long leg of the triangle, is equal to AC, which is the hypotenuse of the mid-sized triangle, over AD, which is the long leg of the mid-sized triangle. All right, example 2, using the geometric mean. For A and B, we have to find the value of each variable. In A, I'm actually going to use Theorem 9.2. The reason why I'm using Theorem 9.2 is because I have to find the altitude over here of the triangle. I'm going to redraw this mid-sized triangle so that it matches up with the little triangle over here. So it's going to look something like this, and it's not going to be drawn to scale, obviously. Going to rotate the mid-sized triangle about 90 degrees clockwise so that I have X at the bottom over here and 8 over here. And this is my right angle. So now I can write my proportions. I have 8 over x is equal to x over 4. Cross multiply, I got 8 times 4, which is 32, and x times x, which is x squared. Solve for x by taking the square root of 32. 32 is not a perfect square, so I'm going to simplify this. 32 divided by 2 is 16. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. Every pair that I have, I'm going to take one of those guys, get rid of the other, so it's 2. I have another pair over here, take one, get rid of the other, so it's another 2. The lonely guy goes back home. 2 times 2 is 4, and I'm left with 4 square root of 2. In part B, I have to use Theorem 9.3 because here I'm finding the side lengths. In this case over here, this little triangle I'm going to redraw so that it matches with the big triangle. If I redraw it to match with the big triangle, my hypotenuse is y, and the short leg of my triangle is 2. So to write the proportion, I've got the hypotenuse of the big leg, which is 6 plus 2, over the short leg, which is y, is equal to the hypotenuse of the little triangle y over the short leg of the little triangle 2. I can simplify this one. 6 plus 2 is 8 over y, and y over 2. Cross multiply, you got 8 times 2 is 16, y times y is y squared. Take the square root of both sides to isolate y, and square root of 16 is 4, so y is equal to 4. Alright, checkpoint problems number 3, 4, and 5 are yours. For each of these questions, please find the value of the variable. Alright, that's it from me. I'll see you all soon.